And I'll blow it up. I'll take a chunk out of the middle, and it's a reverse return header system buried in the ground with a 3-inch supply, a 3-inch return, 1.25-inch loops. It's all DR11. The loops go to a depth of 495 feet. So now that you've seen it, the question is, what's wrong with it? And this is the quiz. I'll try to go back, take another view. And this is from a real job. Too many loops in one circuit, we get a vote for. Difficult to flush and purge. We'll go back, take another look. And details like this on a set of engineering documents disclose a lot about the experience and the competence of the designer. So we got to be careful sometimes in the details we put in drawings. And contractors who look at this, experienced contractors, will start to doubt the efficacy of the whole design. So details are important. And we seem to be closing in on two prime suspects. There are too many loops in the circuit, or it will be difficult to flush and purge. Any other opinions? Loops are too deep? That's an interesting question, because 495 feet is indeed deep. In New York State, if you go deeper than 500 feet, we have to get a permit from the Department of Mines. And we'd like to avoid that. So we pretty much narrowed into one of two suspects. And I'm going to guess that it's the contractors who see this problem and perhaps the engineers who see too many loops in a circuit. Because the real problem is flushing and purging. And there are other little problems, and I'll talk about those too. But to flush and purge a buried manifold in that configuration, I'm looking for even those experienced contractors to tell me, what do you think it's going to take to flush and purge it? And I get nobody willing to put forth a guess. Okay, the jury's coming in. And indeed, it's heavily weighted to the astronomical number. And let us go through a little bit of the math. To calculate a flow rate that corresponds to that minimum velocity of 2 feet per second, which is what we need to move air bubbles through a pipe. It can actually move air down a vertical leg of a loop and push it up the other side. So that's our minimum velocity that we need in every section of pipe. The tricky part is keeping track of all the units and conversion factors. Basic formulas: flow rate in cubic feet per second equals cross-sectional area of the pipe in square feet times that velocity we want. So 2 times the area will give us cubic feet per second. And then we got to do a bunch of conversions. And we develop a table, and we'll look at these smaller sizes, 3/4 through 3 inch. We calculate that cross-sectional area in square feet. And then we start converting again with 7.48 gallons per cubic foot, 60 seconds in a minute. We can now calculate the minimum flow rate we need to achieve this 2 feet per second. And we can see that this 3-inch section of pipe needs over 40.159, or call it 40.2 GPM. And although this loop could be purged with 9 GPM, this section of the manifold has to have 40. Therefore, the loop must also have 40. Every loop will be roughly equal in flow rate. So 40.2 times 17, 683 GPM. That's a big pump. But the story is not over. Because if we have to pump 683 GPM, what is the pressure drop that loop field will present, that pump has to overcome? We look at each individual loop. And for the 40.2 GPM, we merely calculate for one loop because they're all in parallel with each other. We only have to calculate one. Calculating pressure drop can be tedious unless you utilize tables that provide a pressure drop per 100 feet of pipe, typically expressed as feet of head per 100 feet of pipe. The loops are 990 feet long with a U-bend at the bottom and typically 2 elbows at the top. So simply rounding up to 1,000 feet is appropriate and frankly a lot easier to manipulate in your brain. Do not get discouraged if you cannot find a table that provides the exact flow rate you are looking for. You can always adjust the pressure drop by this formula. And anybody who's calculating pressure drops, this formula should be second nature. You take the ratio of the flow rates, square it, multiply it by the known pressure drop, and you get a new pressure drop. It's very simple. If I double the flow rate, 2 squared is 4, my pressure drop goes up by a factor of 4. There are many tables and calculators out there. Just be careful to get the DR11 high-density polyethylene table. There's a website that I found that is very helpful that gives you all the different choices of materials and flow rates and fluid, but we're going to be working with water when we're flushing and purging, so that's what we want to look up. Per the formula above, we can calculate the pressure drop at 40.2, even though the 36 GPM table said it was 16.69. We take that ratio, we square it. Our loop will have a pressure drop of 20.81 feet per 100 feet. We then multiply by 10 to get a pressure drop of 208 feet. Now we're multiplying by 10 to account for the vertical difference between the top and bottom of the bore. Is that a true statement? Okay, I think everybody's paying attention. We do multiply by 10 because we have 1,000 feet. And we calculated the pressure drop in feet per 100 feet. So 1,000 is 10 100 feet. Now we can calculate the pressure drop of the header itself by looking at each 20-foot section of pipe that progressively increases in flow rate from 40.2. We add another 40.2, we add another 40.2, and this table illustrates how the last section of pipe is at 643, and the going to and from the vault would be another 40, or 683. But we got to look at this manifold. What's the pressure drop of it? So we use since we've got a 3-inch pipe for the entire length, we're going to use our reference pressure drop of 10.7 feet per 100 feet at 200 gallons a minute. We then do the math. We have a flow rate, we have our reference flow rate, we have our reference pressure drop. We take the square of the ratio of flow rates. We calculate an adjusted pressure drop in feet per 100 feet, but since we've only got 20 feet of pipe, we multiply by 0.2, and now we see the pressure drop through every section of that 16-section manifold. We've got 2 manifolds, so we multiply the total by 2. So that 3-inch pipe going down one side and coming back the other will create a pressure drop of 258 feet of head. Now we got to look at the 3-inch pipe going back to the vault or a building where our purge ports are located. So we look at the length of that 3-inch pipe, and again we use our reference pressure drops. We estimate on this job we had to go about 540 feet. And at 683 GPM, the pressure drop for that supply and return pipe is nearly 674 feet of head. We now have to add the loop, the headers, and the pipe to get a total pressure drop of 1,141 feet, or 488 PSI. Now this next question might be a little facetious, but I'm curious if there's any design professionals out there that think we can even get a pump capable of 683 GPM at 488 PSI and actually flush and purge this system. And yet this is a real design put out in bid documents, and contractors were expected to bid on it, and they sat there and scratched their head. I had many of them call me and simply say, I won't bid on a job that I have no faith is designed right. Frankly, it would take 2 fire trucks to flush and purge this system. Even if you could, would you want to get a pump that big? Let's think about that. Considering that DR11 pipe made from PE 4710 resin, which is the latest and strongest plastic resin to use for HDPE, has a nominal rating of 200 PSI, and at the bottom of the loop you have to add another 500 feet of water column, or 214 PSI. So already with the static water in the pipe, we're right up to design pressures of that loop. Now we're going to run roughly half the pressure drop will occur before we get to the bottom of the loop. So half of our 480, we have to add another 244 psi and subject the pipe at the bottom of the borehole to 458 psi. Now, granted, there is some safety factor in polyethylene pipe. Burst pressures are typically 600 to 800 psi, but we certainly do not want to be subjecting them to this kind of pressure. And if that isn't bad enough, I hope someone out there noticed this, the dark cloud hanging over the design. This illustrates that the designed flow rate in each loop is 3 gallons a minute. Let's ponder this. I got a depth of 495 feet with an 1.25 inch loop. Does this mean we need 495 feet per ton? Or are we deciding to run a very low flow rate per ton? Or maybe the engineer just really didn't know what he was doing and didn't ask anybody. Implications. With that kind of low flow rate, you've got extremely poor Reynolds numbers, so our heat transfer will be very poor. Now, the loop itself may be so oversized at 495 feet per ton that we could get by with water only. But frankly, in our neck of the woods, it's not a wise move. Some additional information on this job. It's a typical K through 12 academic building, about 100,000 square feet. The load is about 300 ton. And guess what? There are 284 loops in the loop field. And perhaps the engineer actually believed what our industry has misguided us in thinking. All too often I hear the phrase, 1 loop per ton. And nothing could be further from the truth. So it's shame on us. Our industry has promoted that for years. And in the Northeast, we are rather unique. We tend to want to go deep. We'll put 3, 4, even 5 ton on a loop. Implications. I can only conclude that the engineer failed to fulfill his or her responsibility to the client and ended up making the client spend $3.1 million on a loop field that should have cost about $1 million. And that is how geothermal gets labeled as being too expensive. The good news, the engineer admitted to making a mistake and changed to a reducing manifold design. And he called out a sufficient amount of 2.5 inch pipe. Now, you experienced guys in the audience, how many of you actually use 2.5 inch pipe? Okay, I want that guy who's using 2.5 inch to stand up and tell us where he gets his fittings. Because that is the real shortage. Any pipe extruder would be glad to extrude you 2.5 inch pipe. Because frankly, they don't care how you connect it. But there are no fittings readily available in the geothermal industry that can accommodate 2.5 inch high density polyethylene. The same is true for 5 inch. You just cannot find them. And there's no point in burdening a project with custom built fittings of any kind. We can live with 2 inch or 3 inch or 1.5 inch, 1.25 inch. But to specify 2.5 or 5, again, illustrates a lack of experience. Click. Moving on to the next, the second act of my 3-act dissertation today. What's the difference between an egg and an elephant? what's the difference between a short loop and not sizing pipe for efficiency?